I will begin today with an exercise in ultrafiltration, and then afterwards we are going to do another exercise, which is the last one for the semester in electrochromatography. And then at the end of the class, I will give you a few tips for the presentation and report for your PBL and small information about the exam. All right. Let me just share my screen. You see now the slides in ultrafiltration, right?
Yeah.
Okay, that's good. I unfortunately somehow for this link have the people need to be admitted. So I might be checking a little bit on the participant list to see if somebody is maybe joining later. But yeah, I don't think, so I'm sorry if I interrupt for a moment, but that's, I guess, fine. Okay. So you've already had two classes with the topic of filtration, so I will not go now into too much detail. What you should know and what is also important for your exam is to know some basic characteristics between the different membrane processes that you studied about and to know how to distinguish them. Yeah, basically, yeah, so this table that I'm showing you here is quite important. It can come as a question in an exam. Of course, not the whole table and not all unit operations, but you should know, as I said, what are the basic types of membranes, selectivity principles, and driving forces, and also how to sketch the given operation. Today, we are focusing on an ultrafiltration, which is a liquid-liquid separation, and in this case, we have a porous membrane, which is normally an asymmetric and quite frequently a composite membrane. And our solvent is passing through, while the dissolved components are being retained by the membrane. And the mechanism or the principle of separation is the size inclusion. So the molecules that are large enough or larger than the pore sizes of our membrane are going to be retained, while the rest is going to go through the membrane. There are different modes of operation and also different apparatuses that we can use in ultrafiltration. Here, as you see in the picture, so this is not exactly the ultrafiltration, but what we see is the inside out type of operation, where our feed stream is going through the bundle of tubes and diffusing toward the outside. The other possible way is to have the vice versa. So if, let's say, we have our tubes like this, we can have our feed also flowing in between, and then our filtrate going out from the inside of the tubes. Which mode, each mode, of course, has its own advantages, and which one we're going to use depends on the system. So if we have an outside in operation, we are a bit using a larger surface because we have here an outside diameter is a bit larger than the inside. However, yeah, then again, for some systems, it might cause higher pressure drops and maybe more difficult for cleaning. In this case, normally aeration is used as a cleaning method, or backflushing, and if we have an inside-out operation, then we can also use some form of chemical cleaning, etc. We can use different apparatuses. There is a spiral one apparatus, as well as a tubular and hollow fiber modules. The differences are it is usually a trade-off between the surface area. So in case of, let's say, hollow fiber module, we have much smaller tubes, but then, and of course, a higher surface area for our operation. But then these thin tubes are also more easily breakable. We can have here a larger pressure drop, more difficulty with cleaning and fouling, and so on. As I mentioned, the membrane itself, in case of ultrafiltration, is an asymmetric membrane. So usually, let's say if we say it's a composite membrane, we would have porous support, which has quite large pores, and then a very thin layer on top, which is actually determining our which has the pore size required for the operation. And in this way, if we have a small and a thin porous layer supported by a stiffer layer with larger porosity, we can minimize the pressure drop and still have quite large separation efficiency. So the molecular weight cutoff for ultrafiltration is usually 1 to 1,000 kilodalton, and we normally have around 90% rejection level. I'm sorry, this is not so responsive to me wanting to go next, so I'm sorry if there is a bit of a delay. Okay. If you look into your sheets, and I hope that you have them either printed or in the PDF form on your computers, I have uploaded both to StudIP, so both for ultrafiltration and electrochromatography. So if you haven't already, please open them and have them before you. And this is a drawing that you can see on as well on your exercise sheet. So what it is showing is, so this is our membrane, and here we have a flow in a crossflow operation. The concentration inside the tube here termed as CC. So we have one concentration in our feed. If we look into an area close to the membrane, we will see that there is an increase of concentration towards the membrane, and this is called the concentration polarization, which creates this laminar layer at the membrane surface. And so basically, not all molecules cannot pass through, and we have back diffusion towards, again, to the feed side. And then the molecules that can go through are passing and going to the permeate side, and here this is noted as CP. If we write a mass balance at a steady state, we have, so this is a mass balance for our, let's say, target component. So the mass on this side of the membrane, so this is the flux on the feed side and the concentration in the feed, plus this is the accumulation. This part is the accumulation at the membrane, so the back diffusion. And here we have minus because this is what is going out of our system. So this is the mass that is going through the membrane. And they need to be in equilibrium. this flux is so the flux through the membrane is directly proportional through the transmembrane pressure and depends on the pressure difference across the membrane. However, since we have this concentration polarization and back diffusion, we also have creation of an osmotic pressure that is working against which is working against our which is working against the transmembrane pressure and reducing the flux. All right, so these are the two fundamental equations that we will be starting with. All right, so in our task, what we have is an apple juice that we feed into an ultrafiltration tubular mode. We have a feed that is flowing inside our tubes. So we have an inside-out operation, and then we collect the permeate outside the tubes. This apple juice contains pectin, which is our compound that we are retaining, and it is accumulating at the surface, and this causes the formation of a gel layer when the pectin concentration reaches the concentration of 45 grams per liter, which we want to avoid. The velocity of our juice inside the membrane is 1 meter per second, and the diameter of the ultrafiltration tubes is 1 centimeter, and the length is 2 meters. The concentration of the pectin in the feed is 5 grams per liter. And now we need to determine the flux of the clarified juice. I will give you a minute just to have a look. Or no, actually, we can maybe go through this together. So, as I mentioned on the slide before, we had this mass balance equation. Now, if you integrate this differential equation, maybe you can also try to try it yourself, but you should get this form shown here. In this equation, K is the mass transfer coefficient, Cm is the concentration of the pectin at the membrane, which is given here as 45 grams per liter. Here is the concentration in our permeate stream, and Cc is our concentration on the feed side. Now, we can say, or we can assume that if we assume 100% retention, or that this concentration at the permeate site is negligible, then our flux can be calculated in this way. So we have the mass transfer coefficient, which multiplies the natural logarithm of the difference between this Cg, or the maximum allowed pectin concentration, and Cc, which is the feed concentration. So we have these two concentrations given in our task, and what is unknown is the mass transfer coefficient. Now, if you look further on your sheets, you have given different dimensional numbers that we normally use to solve the mass transfer issue. And what is important here is the Sherwood number, the Reynolds number, and the Schmidt number. If you look into our Sherwood number, you will see that in its formula, it contains the mass transfer coefficient. So we have the mass transfer coefficient multiplied by the hydrodynamic diameter of the module over the diffusivity. So this is what we need to calculate. So this is what I just mentioned. And to obtain the Sherwood number, if you take a look into equations 2 and 3, we need to use Reynolds and Schmidt numbers. And which of these two given equations we are going to use is going to depend on the value of our Reynolds number. I'm sure that you're already very familiar with these dimensionless numbers. So I give you maybe 2 minutes to try to calculate this by yourself. And then we do it together. Try to do independently as much as you can, and then I show you the results. Somebody is asking, when using asymmetric membranes, should the smallest pore size face upstream or downstream? I imagine you mean here the feed or the permeate side. So I will answer accordingly. So yeah, it should be on the feed side, and then you have the support towards the permeate side. All right. Let's see. So you should have obtained the Reynolds number of 8,500, which means that we need to use the equation 3 then to calculate the Sherwood. The Schmidt number, so all these values are given in the task. So the dynamic viscosity, the length of the module, the diffusivity, hydrodynamic radius, etc., etc. So it's basically just introducing the values into the equation. And I believe that you have found all these values. So in the end, for Reynolds, you should get 8,500. And for the Schmidt number, you should have obtained 1.47 times 10 to the power of 4. So yes, as I said, the Reynolds number of 8,500 is going to tell us that we need to use equation number 3. So if we introduce these values into equation number 3, you should get the Schmidt number of 784. And from there, then you can easily calculate the K value, which be 6.072 times 10 to the power of -6 meter cube over meter square second. I leave this for a minute so you guys can copy or double check your answers. And then I will show you the flux calculation, because then again you just have a formula and need to insert the value. So we just need to see the solution. And then the flux. So if you now use this value for K, and as I said, our concentration at the membrane, for this we take the maximum concentration that we're allowed to reach over the concentration in our feed. And this should give us 1.33 times 10 to the power of minus 5 meter cubes per meter square second. And if we want to transfer this to liter, you will get 48.01 liters per meter square hour. Are you catching up? Or am I a bit fast? I just want us to have enough time for both exercises. And also, I think this is not hard, at least not the exercises we have today. And of course, as all of them, these slides will be available for you on StudIP. So then let's go on to the task B. Now what you should do is calculate the number of tubes if the desired permeate flow of clarified juice is 100 liters per hour. I give you 2 minutes to try to solve this yourself. A small, just a hint. So you have the volumetric flow rate. You also have your flux, also in liters meter square per second. What you can obtain from this is the area, the total area that you need for the whole module, and then you have the size of the tubes, and from there you can calculate it by comparing these two areas. You can calculate the number of tubes that you need. So yeah, in 2 minutes I will share my slides, my results. All right. So as we calculated previously, our flux is 48.01 liters per meter square hour. And we have here the volumetric flow of our permeate to be 100 liters per hour. Now, as I told you already initially, you can calculate the total area that you need, the total membrane surface, based on these two values. So by dividing the volumetric flow and the flux, which is basically the flow per area. And you should get 2.015 meters squared. Now this AM is the area of the module, so the total area of all our tubes. And to calculate the area of one tube, we need to divide this off the area of per tube. It is given in our task that our tubes have the diameter of 1 centimeter. So this is 0.01 meter. And the length of 2 meters. So this is the area of the whole module. This is the area of the tube. And in the end, you should get approximately that there should be 32 tubes. All right. Any questions to this? Or to anything by now? All right. The third task that we have for ultrafiltration is to calculate the necessary pressure difference, delta P, if the given correlation here for the osmotic pressure can be applied. So from this, you can calculate the osmotic pressure. And then if you look into equation 4, you see an equation for delta P, which represents the pressure going across the membrane itself. And it is equal to the differences between the pressures. So I have it here. Oh, no, this is the solution already for the pressure. So I will let you guys do this by yourself. But if you look into equation 4, let us first calculate the osmotic pressure, and then we go on to calculating the pressure difference. But for those who did this already and can do it quickly, you should calculate the osmotic pressure and then go on to the equation 4. And in 1 minute, we do it together. All right. So if we take this equation, so this Cm is basically the concentration of our at the membrane. So we use 45, and the rest are just the empirical coefficients. We should get, or you should have also gotten 3,840 or 41 pascals. Now, as I also mentioned, this is delta P is the driving force for the flow of from the flow from the feed to the permeate side, and it is equal. So we can calculate this pressure difference. This is the pressure inside our tube, and this is the pressure on the permeate side. Inside our tube, we take it as the average pressure between the inlet and the outlet, because we will have some pressure drop. And this is just the pressure at the permeate side. This is also equal to the flux times the membrane resistance plus the delta pressure, which is the osmotic pressure, the delta pi, which is the osmotic pressure. So our total pressure difference across the membrane is, so we use this right side of the equation. We have calculated the flux. So if we convert our 48.01, that was in liters per meter square second, but now in this equation we need it in the form of meter cube per meter square second. This is our membrane resistance, which has the unit Pascal second per meter, plus the osmotic pressure. You should get 43,740.9 pascals. Sorry. All right, I leave this for 1 minute. Is everything so far okay? And do you guys have any questions? All right, you can also write the questions down or email me later if you come up with them, of course. Yeah, I'll leave this now for a minute, and then we start with a new exercise with electrochromatography. All right, I will end this presentation then and begin the capillary electrochromatography. You can see the presentation, right? It says capillary electrochromatography.
Yes.
All right, great. Good. So, I believe you as well heard in class from the professor about electroseparations. I'm not sure how much he mentioned it in the context of chromatography, but the principles are that we need here and also for this task are nevertheless the same. So capillary electrochromatography is based on the principles of capillary electrophoresis and high performance liquid chromatography. So capillary electrochromatography has higher efficiency than HPLC. In this case, also if you remember, we have a plug electrophoretic flow instead of this parabolic pressure driven velocity profile, which we see in HPLC. And this is very beneficial and has positive effect on the efficiency of our separation and, of course, minimizes the peak broadening. So it goes as follows. The system has just a second, has two buffer tanks. One is the source vial when we have the mixture of our target components at the desired pH. This is our capillary. Normally, this is a silica capillary most frequently. Then it has another vial, which is a destination of vial into which our target solution flows. And on its path, it passes through a detector where the information is collected about the composition and the flow of our solution is going from the anode to the cathode when we apply high voltage between our electrodes. So this is how the system practically how it practically looks like. Now in capillary chromatography, we have movement of ions under the electrostatic force, and we also have the movement of the bulk fluid together, which is kind of caused by the movement of those ions. So we distinguish the electroosmotic flow, which is, as I said, the flow of the whole bulk fluid due to the motion of ions. We have, in this case, electroosmotic flow has a direction from our anode, which is a positively charged electrode, to our cathode, which is a negatively charged electrode. And in all systems that use silica capillary or unmodified silica that have negative silanol groups, and then this positive layer of ions in between, it will always have an electroosmotic flow in the direction from positive to the negative electrode. So yes, we in this way. So we have, let's say, in our solution, different cations, neutral compounds, and anions, and they will have different components of velocity based on their charge. So if we have, as I said, this situation in which our fluid is moving, if we say this is our positive direction, so our neutral compounds since they are not attracted neither to anode or the cathode, they would only express or move due to the electroosmotic flow. And their apparent mobility here called EM is going to be equal to this. Our cations, so our positively charged ions, are going to be moving in the direction of the flow towards the cathode. So their velocity components are going to be consisted of the electroosmotic flow and the electrophoretic mobility. So due to the mobility, due to their charge, right? So their apparent mobility is going to be a sum of these two, and they will have the fastest movement inside the system. And then, of course, anions have the opposite situation. They move in the positive directions due to the electroosmotic flow, but they are more attracted to anode. So their total velocity is going to be reduced due to this. Of course, the velocity of the electroosmotic flow is going to be larger, so in the end, they will also be going from the anode to cathode, but it's, as I said, their velocity is going to be reduced. All right. So now that we've went over some basics, let's see how our problem looks like. So today we have three different components in our system, which are p-hydroxyphenolic acid, p-hydroxybenzoic acid, and benzoic acid. In this table, you can see, so also if you have a look on the page 2 of your sheets, you also have the peak diagram, which shows us how the spectra or the peaks that we got from our, the signal that we got from our compounds. And as you see, and these values in the table are just summarized for you, so you don't have to actually measure them with your ruler and everything. Yeah, thank you for informing me that somebody's waiting. I'm trying to have a look, but yeah, I need to close it to see my presentation. Here are just, as I was saying, here are just the values from this diagram summarized for you from the chromatogram. So you have peak area given, peak height. Of course, this is the experimentally determined migration time. This is the average valency or the average charge value for these components and their molar mass. So yes, as I said, we have these three components that we need to separate, and they have their which are both negative, all three negative in their valency, and also we put inside a neutral marker, which has no charge. We will see why. There was no pressure applied in this process. The electric potential was negative at the entrance and positive at the exit of the capillary. So now the task 1, maybe actually before I read this, you guys can go ahead and open your PDFs and read the first page. And then in 2 minutes, we do it together. All right, then let's begin with the first task. I believe you've already skimmed through all the equations, and we are gonna go over them as we are solving the test, so you will understand better. So the first task is to calculate the electroosmotic mobility if the applied voltage is 25 kilowatts. The total length of the capillary is 47 centimeters. The detector is situated 3 centimeters before the end of the capillary, and there is no significant retention of the neutral marker. So what does this mean? So neutral marker, as you remember this picture from a little bit before, which is not charged, his velocity component is not going to have the electrophoretic velocity components. And this means that here, if you have a look into equation 1, this is our total velocity, which equals to the sum of the velocity due to the electroosmotic flow plus the velocity due to the electrophoretic flow and the velocity due to the applied pressure gradient. In our case, we are not applying any pressure, and if there is no retention of the neutral marker or no significant retention, then we can also say that the electrophoretic flow velocity is as well 0. And we can use this neutral marker to help us determine this electroosmotic flow velocity. And this electroosmotic flow, as we said, it's the same for all charged or non-charged species. It's also only going, the observed velocity is only going to be changed depending on whether it interacts with the column or not. So we can use this neutral marker to determine our electroosmotic velocity. So what is important for this task is our equation number 1. Also, if you have a look into equation number 3, you can see we can connect the electroosmotic mobility, which is, I believe, here given as a value, or no, we calculated just a second. Never mind. So here we have electroosmotic mobility, which is equal to the electroosmotic velocity times this is LT is the total length of the capillary, which is 47 centimeters, and U is the voltage. And we have equation number 2, if you have a look, which is here termed as a velocity of a retained compound, because we have this U0 over 1 plus the retention coefficient. But if we here, instead of the migration time, we can use the migration time of an unretained component. This can be useful. We can say that this is our electroosmotic velocity. Okay. Sorry. Yes. So now you can proceed, and so you need to calculate the electroosmotic velocity, and then from there you can calculate the electroosmotic mobility. Try to rearrange these 3 equations, and then we see in 2 minutes how is the solution. So basically, just as a further hint, you need to actually, because this equation comes down to only electroosmotic velocity component. So basically, you need to use only equations 2 and 3. And if you express this electroosmotic velocity by the equation 2, you can directly calculate the electroosmotic mobility. All right. What you should obtain is, so as I mentioned, we need to calculate the electroosmotic mobility. If the applied voltage is, which is given, so this value is given, we have the total length of the capillary, which is LT. We have the effective length of the capillary, which is the difference between the total length and this, because our detector is actually before the end of capillaries, so this is where our components are detected. So this is what we call the effective length, and yeah, so this we have the voltage and the time necessary for the unretained compound to pass through the column, which is given in the table on the page 2. So we have 1.72 minutes migration time for our neutral marker. And taking all these values, you should get that the electroosmotic mobility is 0.048 centimeters square per minute volt. All right. Under our second task is to calculate the electrophoretic mobility for the analyte 2. And this is also quite easy. So electrophoretic mobility of our charged components is going to depend mainly on their charge and on their molar mass. And this is given by equation 4. And I believe already all these values are given. And I think you can already substitute everything into equation 4 directly. All the values are given with the text. Yeah, just pay attention that you use the right valency for the task. And then in 3 minutes, we do this, I show you the solution. All right, so I believe this is quite short and quite easy. So for the electrophoretic mobility of analyte 2, which is our P hydroxyphenolic acid, you should have obtained 8.9 times 10 to the power of -3 centimeter square volt per volt minute. Now under 3, the third task for today is to determine the retention factor for the same analyte. So for analyte 2, if you pay attention to equation number 2, here we have the velocity of a retained compound. Yes, so equation number 2. And here is where our retention coefficient configures. If we rearrange this, we will get that the retention coefficient equals the velocity of an unretained compound over the velocity of a retained compound -1. So in case this U0 for our analyte 2, we can calculate from the equation 3, and also UR we can calculate from equation 2. Try to rearrange these 3 equations to obtain this K value for analyte 2, and I give you a few minutes and then we try to go for it together.
Can you please go to the former page? I lost some lines.
Okay, then I go for a minute to the previous page. The ones who are past this, you have all these equations in on your sheets, and I just go very shortly to the previous page and come back. But also, if you don't manage to write something down, this is all going to be on StudIP, so that is also fine. All right, sorry, I will go forward, but you can find this on StudIP. I will upload it right after the class. So by rearranging these equations, so actually by introducing equations 3 and 2 into this form of equation 2, in the equation for expressed retention factor, you should obtain this. And from here, we have all the values already necessary to calculate our retention coefficient. So in the end, you should get that the retention coefficient is 0.8160. Are you managing to keep up? All right, I take that it's okay. So this is our electroosmotic mobility, which we calculated under the first task. This is our electrophoretic mobility, which we calculated under the second task, and all the other values are given in the text or by the task. All right. I assume that you already managed to calculate this by yourself or to copy the solution. Let's go to number 4. So under 4, we need to calculate the resolution of the column for analytes 3 and 4. And this resolution is a very important factor that usually characterizes the quality of our separation, and yeah, it basically tells us how distinctive our peaks are. So we can calculate it as from this formula, which considers the retention times and peak widths. Peak widths are not directly given in the table, so these are all the residence times you guys have. But the peak width we can calculate as 2 times peak area over peak height. And peak area and peak height are both given in table 1. These are all experimental values. So try to calculate this and then this from those two values for analyze 3 and 4, and then after a minute I show you how it should be. All right, so for the peak widths, of course, here we have time. So we also express it in time. You should have obtained 4.61 seconds for peak 3, for width of peak 3, and 4.68 seconds for the width of peak 4. And if we put this together and to calculate the resolution, you should obtain 1.68. That is the resolution of the separation between these two. All right, now this is quite easy and will be available, as I said, online. So I will go on to the final task. So in our final task, we need to calculate the heat flow introduced by Joule heating. And Joule heating is the heating generated due to the movement of ions. So these, in capillary electrochromatography, one of the major drawbacks of these processes is actually this heating effect. And it is not good because if we have a heating in our system and we cannot predict it or we cannot control it, then of course the temperature changes, the properties of our of inside our system changes, the viscosity, the retention times, and this all affects the separation efficiency. And also with all this, And if it's not as controllable and predictable, our separation and our results, our separation is not reproducible, and then our results are not as reliable. So this is something that needs to be taken quite a bit of care of during electrochromatography and similar processes.
Excuse me, can you go back to slide, previous slide?
Mm-hmm. Yeah.
So is that W3, is that 198 or 11889? 2 into 0.198, but it's actually 0.189.
Yeah, sorry, it's my mistake. Double check the value just in the end, okay?
Yeah.
But it's all from the table values. Yeah, thank you for letting me know. But yeah, just double check this final values. All right, so back to the heat. So we have this Joule heating, and we have given here the size of the capillary with inner diameter of 75 micrometers and the outer of 375. The conductivity of the solution we also have. So we need to calculate what will be the average temperature increase during the separation if we have the loss of heat of 80% and the volumetric heat capacity of 2,100 kilojoules per meter cube Kelvin. The initial temperature is 25 Celsius. Now we will do this together, and then I will leave you some time to copy. Just to be faster for today, because there is some stuff also I want to show you regarding the exam and some tips for PBL before, and I know you have the class for with Professor Johansson. So I will just proceed with this. So you also have this equation given. So this is the flow of heat generated during the process. K is the electrical conductivity. It is given here to be 0.05 millisiemens per centimeter. Then V is the inner volume of the column, because our heat is generated inside the capillary, because that's where we have our solution and ions. Yeah, this is our electrical field strength. We can rewrite this a little bit and to write E, or electrical field strength, as the our voltage over the total capillary length squared. These are again all the values that we have given by the task. So 0.05 times 10 to the power of -3 Siemens per centimeter, -3 because here we had milli. This 75 times 10 to the power of -4, this is, if you see here, the inner diameter times P over 4 to get the volume. And this 47 centimeters is the, this 47 centimeters, it's all part of the volume to get the volume of the capillary. So the 47 centimeters is here, its length, and this part comes from this part of the formula. So this is voltage, and again we have the length of the capillary, all this squared. And you should, so depending on how you round the values, but here you should get 0.029 watts. So this is joules per second. So this is the heat generated per unit of time inside our system, and this is given by the equation 8. Now, to calculate the total heat, amount of heat that is generated inside our capillary over the duration of the process, we of course need to know how long we have done the separation. And here, so we need to, since this is watts, which is joules per second, this is the maximum migration time. This is because this is the maximum time that the heating is taking place, as the maximum time that we have our analytes inside. And this 1 minus 0.8 is because we had 80% loss. So basically we just take the 20% that are remaining in the system. So we have this is the flow of heat that we just calculated, 2.93 minutes. This is the, as I said, the longest migration time which we obtain for benzoic acid. The 60 is to convert between seconds and minutes or minutes to seconds. And in the end, you should obtain, or again, depends on how you round, but between 1.2 to 1.02 to 1.03 joules. Now, what is asked from us in the task is the average temperature increase during the separation. And here, just to simplify, now this problem in practice can be a bit more complex because there are different temperatures at different points of the system that you can calculate. If we wanted to calculate the temperature, let's say at the outside of our capillary, then we would need to calculate the thermal conductivity of the fluid, plus then the heat transferred through the wall, which also takes the thermal conductivity and the logarithmic temperature difference over the wall of the capillary, etc. So here we would have at least 2 or 3 components, and our equation would be a bit more complex, which is not the subject here. So we just said, hey, the average volumetric heat capacity of the system is 2,100 kilojoules per meter cube Kelvin. So for this, you can only use the basic equation for heat transfer, which is, so the total heat, so this is this heat that we generated in the system, can also be expressed as the volume of our capillary times its volumetric capacity of everything included, times T2 is the temperature at the end, so final temperature after our system has been heated, and this T is the initial temperature, which we assume here is a room temperature before we started the separation. All the values here are given. Here, pay attention, we are using the outer diameter because we're taking into consideration the whole volume of the capillary. Since it's the walls and everything is also heated. This is our capacity. We need to convert kilojoules to joules. And yeah, everything is given by the task. And of course here, plus initial temperature, which is 25 degrees. And you should get that the final temperature is 34.44 degrees. Now I leave you 1 minute to copy this, and then I will go on to say a few words about the PBL and exam and tips also for the presentation and everything. All right. If you haven't, this will be, as I said, online after we finish today. I have announcements for everybody for the final PBL presentation. Professor and I spoke, and we would shift it from January 24th, as it's stated in the schedule, to January 28th. So instead for this Friday when we should actually have the exercise slot. Does anybody pose or knows why not to. Normally, this is the slot which we have and in which we should have had the exercise. In this way, we think you can have a bit more time to do it better. And also we have normally more time on Friday and you will have quite long presentations. Is this okay for everyone?
We have a oral exam for thermodynamics.
On Friday?
Thursday and Friday, we haven't been given the slots, but they'll be divided.
All right. Then I will speak once again with the professor, but this is strange. I think, I don't know when, do you guys know when is the official date where the semester should end?
Yeah, it's actually the 29th. Yeah,
This is-
29th of January. They programmed the exam for those 2 days, 27 and 28. But as my colleague said, we haven't received the slot. So I don't know.
Because yeah, that is a bit strange. The exam shouldn't be within the lecture time, and we do have a lecture on Friday. I mean, we should have this appointment, and I think it's better for you to. I mean, we have. Do you guys have anything on Monday? Any lectures after art class? No.
No.
So in principle, it's not the problem. I remember somebody left this Monday. And I know on Friday, because that you normally would have a thermodynamic at 2 or so. So we felt that Friday is just kind of better. Okay, then I speak with the professor. If you guys have exam, then we definitely leave it for 24th. Yeah, this is weird from the thermodynamic guys. But I might also check with them, but I don't think they will move the exam either way.
Okay.
All right. Okay, but then we leave it for 2024. If I don't send any information to you, then it's 24, and if we decide to change it, I will let you know. Yeah. So further information: the duration of your presentations should be 15 minutes for each group, plus 5 minutes discussion, so 20 minutes in total. You need to send me your presentation at least one day before to my email. Deadline for the reports is March 1st at 7 a.m. and you need to send me PDFs via email, also supported with your calculations. So I prefer Excel sheets. I will open the presentation with a bit more feeds just in a bit. It's all gonna last short. Short information for the exam. It's going to be, as I saw in the schedule on March 16. I haven't seen to my last information that they published the room or the time, or the time. So just the date. And in general, you can have only calculators with you and a ruler. You cannot have any of your sheets or any other material. We are giving all the sheets for writing and also for the task. We will upload test exam to StudIP, and there will be a special consultation hour dedicated to exam preparation later when the exam comes a bit closer. Of course, before that, we can always schedule the consultation, per email, or you can always write to me. But there will be one official one where you will be all notified, and for everybody, for us to see the exam solution. I just don't know when, but I will send an email. Now, just as tips, mostly I told you guys some main tips last time while you were presenting, but now just to summarize. So for your presentations, so this was usually not the problem. You guys all had a nice font. It doesn't have to be Arial or Grobel. It can be Calibri. It can be something else that it's not too curvy, cursive, and too exotic. But all this like Times New Roman and Calibri and Cambria, this is also acceptable. You should have logo included in all documents. Colors, they do not exactly, they have to be logo colors, but the colors should be kind of similar. The background should be plain. And it's good that the colors are not too off for the presentation slides. So when it comes to the technical stuff, do not have too much text on the slides, so not like this slide. Each slide needs to have a headline, regardless of what is presented, even if it's just one graph, it needs to have the headline. Every slide needs to have one key message. So what are you trying to say? This is important. You shouldn't just present 1,000 things and not have a meaningless slide with a bunch of information. There needs to be a message and the reason behind every slide. This is especially important because you have only 15 minutes and you should really practice well. As I told you also, I mentioned in the class, we will interrupt you if you exceed the time, so you should practice as a group to make it as best as possible. So yeah, roughly a suggestion is, as a rule of thumb, to have 1 minute per slide. Of course, this is not so strict. You can have some slides that are you go through quickly and some that you maybe talk a minute and a half about, but roughly this is how much information you should have on a slide. Keep attention to your fonts. You should have a minimum font size of around 16 points. And yeah, of course, you should need to have high contrast, so don't try blue or black, as we've also seen. So this here you can see how to use a PowerPoint, but I'm sure you know how to. And everything that you mentioned that is not yours needs to be referenced. This font can be really, really small, and it should be at the bottom of the page, but nevertheless, it has to be there. And I suggest citing at the bottom of the page instead of having a separate slide to list all your citations, because yeah, this is more meaningful because if somebody is looking and is interested in what you are showing, then they can see here, and if it's on a separate slide, maybe people forget what is what. Also, you need to have a report, so just a little bit information on that as well. You should use Microsoft Word for your writing, so this is preferable, or something that can give you similar appearance. Everything in your report needs to be labeled, so all the tables and all the figures. So tables are usually labeled above the table, and figures are have the labeling underneath. And all these tables and figures that you have in the report, they should be somehow explained and referenced in your text. So if you put something, then give some meaning to it and explain why it's there. Don't put something just to use space or to cram as much information. You should have, if you have formulas, and you probably will have, trying to explain what you've done, they also need to be numerized as it is demonstrated here. And all the symbols used in the formulas also need to be explained. Yeah, so it's kind of common for different formulas to have different symbols for the same things. That's why we need to explain what we are writing. Literature needs to be mentioned in the text, and in the end, you should have the bibliography, of course. Include page numbers. This goes for both the presentation. So if me and Professor, on your last day on your presentation, if we want to ask you something, then we need to know, we can tell you, hey, this in this slide, we want to know this. Most of you didn't have this in this PBL3 session, so but it is kind of important. It makes it a lot easier for us to ask questions. And yeah, so this goes for both the report and the slides. There is not a preferable citation slide. We don't have a strict instruction, but it should resemble the citation styles normally in all chemical and biochemical engineering journals that you see. There's very small variation between them. I think if you can use, I mentioned this on the first lecture, Citavi or Mendeley or similar programs for citations. And there I think if you just type chemical engineering journals or something, you can get already a pretty good citation slide. And that's all, guys, from me today, all the information I want to give you. I know you have to go to chromatography class. It starts now. If you have questions, I mean, I can stay for a minute or two and answer your questions. Other than that, you can also write me, and I will also give you more information about the consultation that we will have before the exam. It might be sooner, it might be closer to the exam, but anyway, we will for sure have at least one where you will all be invited to. All right, if you have questions, feel free to ask. If not, then I say bye to everybody, and I see you on the 24th then. If not told otherwise, 24th it is.
Is it going to be online on 24th?
I still have to confirm this. So we would prefer to keep it in person, but on the other hand, it's safer for it to be online. So both options are possible. We still need to discuss. You will be notified.
Thank you. Bye-bye.
Bye.
Thank you. Bye.
Bye.